Hello, everyone, and welcome to Session 7 of the Massive Open online course, the MOOC. This is our 10th iteration of the MOOC, and I'm Andreas Antonopoulos, answering your questions from the last week's study. This session is about alternatives to Bitcoin. Our first set of questions is all about Ethereum and smart contracts, and we'll jump right in. As soon as I get a shout-out on the chat room, if you could just let me know whether everything is OK with the audio and video from your perspective. Yay, fantastic. Akis asks a whole bunch of questions, and I'll try and do a quick run-through and introduction to Ethereum to answer these. Akis asks, how are smart contracts actually constructed and broadcast to the network? How does the validation of transactions work in Ethereum? Where is the proof of work? Is gas the corresponding to transaction fees? What is the gas limit? And what are CryptoKitties? Whew. Let's start from the first one. How are smart contracts actually constructed and broadcast to the network? So smart contracts are programs. They're written in a programming language, and it can be a variety of programming languages, such as Solidity or Viper. And there were at least half a dozen programming languages in the past that have worked for Ethereum. And these programming languages are high-level programming languages. Probably the most prolific and popular one is Solidity, which kind of looks like JavaScript syntactically, although it's not JavaScript. Now, how are smart contracts constructed? Well, the smart contract is a software program, but it doesn't run inside a CPU on your own computer. Effectively, it runs inside a virtual machine, which is a simulated CPU. And that simulated CPU is called the Ethereum Virtual Machine, or EVM. So smart contracts run inside the EVM, and they run just like any software program that runs on your CPU, just with a much more restricted environment. And so in order to execute in the EVM, they run as machine code. And this machine code, similar to how you have assembly code running on your, or machine code running on your CPU, and this type of machine code is produced by a compiler. And what a compiler does is it takes an easy-to-read, high-level programming language like Solidity and converts it into a low-level machine language like EVM bytecode, as it's called. So once that's ready, you have your program. Effectively, your program is a very large hex binary string. So what happens with that is you have to register it with the Ethereum network so that it's recorded on the blockchain as a smart contract. And in order to do that, your software would construct a special transaction. And the special transaction has as its destination address the address 0, which is the contract creation address in Ethereum. And as its data payload, it has the hexadecimal representation, or the binary representation, I should say, which you would see in hex, but is a binary representation of your smart contract compiled. Now, once that transaction is processed by the Ethereum system, and it is confirmed, it's recorded on the blockchain, it becomes part of a block. Now, from that point on, your Ethereum contract can run by sending a transaction to it. So that's how smart contracts are constructed and how they're broadcast to the network. Basically, a special transaction going to address 0, and that special transaction has within it, as a payload, the binary of the smart contract, which is being produced by compiling the high-level language. How does validation of transactions work in Ethereum? Well, for simple transactions, which are just payments from one address to another, very similar to Bitcoin, the validation basically processes all of the consensus rules to make sure that the transaction is valid. However, the interesting thing is, how do you validate a transaction that is not a payment to another address, but rather which is a transaction to a contract that causes a contract to run? And in that case, what happens is the transaction and the contract are loaded in the EVM, and the EVM executes the contract and any other contracts it may call, and it makes changes to the data part of the contract. So every contract has some data storage. For example, it might contain a memory segment that has information about who owns a token, or it might have a counter, or it might have something else. And one of those data parts, of course, is the balance of the contract, which is how much ether the contract itself has. And so once that transaction and the contract are run, the contract does something. And what that something is it changes some state. So it maybe changes the balance of an address by increasing or decreasing the balance, or it changes the content of the data. Some memory part of the contract is modified. For example, a counter is incremented, or a new owner is registered, or some other state changes within the contract. All of that information, which is the state as it was before, the transaction and the contract that executed in the state as it was after, is part of the consensus rules. So everybody who is participating in the Ethereum network by running nodes will validate the same transaction with the same contract and the same block in order to see what changes it will make to the state. All of these computers should arrive at exactly the same answer, and that's the consensus answer. That answer, which is what changes happened because of the execution of the contract, is called a receipt. And that receipt is basically the before-after picture, or the change in state that a contract execution caused, or a transaction execution in a contract caused. So that goes to your next question. Is gas the corresponding to transaction fees, and what is a gas limit? Gas is kind of corresponding to transaction fees, only in the simplest case when you're making a payment. More importantly, gas is a way of metering the amount of computation that is allowed inside a smart contract. So as I mentioned before, you send a transaction to a contract. It causes that contract to start executing. And what happens when a contract executes? How do we know how long it's going to execute? How much CPU is it going to use? How many changes to memory is it going to make? Well, because you have an open-ended and flexible system, you can't tell in advance how much execution a contract is going to use. And if you just allowed it to execute for as long as it wants, anybody could create a transaction that basically gets all of the computers on the Ethereum network working forever. Trying to process that one transaction would be very easy to do a denial of service attack. So an important constraint on the entire system, what makes it almost Turing complete, but not quite Turing complete, is a limitation on the maximum amount of processing. And the way that's done is through gas. So think of gas effectively as fuel that goes in your transaction. You put a maximum amount of gas that you're willing to pay, and that gas is counted in units of Ethereum, so it has a price in Ethereum. So you have, let's say you put just random number here. Let's say you say, I'm going to allow up to 100,000 gas to be used in this transaction. And for that, I might pay, 2 gigaway in Ethereum fees for that gas cost. So now your transaction has an upper limit of 100,000 gas. As soon as that transaction starts executing in the EVM starts counting. Every part of the contract that executes has a different price in gas. So every command that the EVM processes, every change to data, every amount of data that's consumed, all of that has a price. There's like a menu of prices in the EVM. And so essentially the EVM is running a meter, and it's counting how much gas you're consuming. The first part of it is the maximum amount of gas that you're willing to put in the transaction is deducted from your account. Then the EVM starts counting, and if the transaction completes successfully, then whatever gas was actually used is consumed as a fee to miners, and the remainder of gas that was not used, which was below your limit, is returned to you. And so that way, the Ethereum network controls how much maximum computation you can make, but it also means, of course, that it also controls how much maximum data you can store, because data storage also has a price. With that, so having said that, what is the gas limit? The gas limit is the limit of the amount of gas that can be processed in a single block across all of the transactions that go in a block. So whereas other blockchains have a maximum block size, for example, in Bitcoin, the maximum block size is 1 megabyte. That limits how many transactions can fit inside a block and be processed every 10 minutes. In Ethereum, there is no limit to the block data size, but there is a limit to the total gas that can be consumed by all of the transactions being processed within a block, and that's called the block gas limit. So that determines how many transactions Ethereum can process in a single block, and it's adjusted dynamically by the miners. So the miners can increase the gas limit in steps by effectively voting for a higher or lower gas limit. All right, I think I covered almost everything. What are CryptoKitties and how are they used? CryptoKitties are a non-fungible token. They're basically a token that corresponds to ownership of a specific digital asset. In this particular case, a cartoon cat. And the thing about these digital tokens is that you can use digital tokens like this to represent a broad variety of things. Non-fungible tokens are tokens that identify unique individual items, whereas fungible tokens are tokens that identify identical items. For example, Ethereum and Bitcoin are fungible tokens. One Bitcoin is the same as another Bitcoin. You don't really need to tell the difference apart. But if you had a token that represented a house, a boat, a car, a CryptoKitty, then that's a non-fungible token, meaning that the token you have represents the specific car, the specific title to a house, the specific virtual cat. And this is basically a game. It's an interesting implementation and a demonstration of the power of non-fungible tokens. It's a game where you have a token that represents a cat. And one of the interesting little twists of this is that you can breed your cat tokens. So if you mix two CryptoKitties together, what you get is a next generation CryptoKitty, which has some characteristics of the two parents. So it's effectively a game of evolution. And by breeding these and buying and selling them, you can play the game. What's interesting about the CryptoKitties application was that it was one of the most popular early examples of a non-fungible token. And it had an enormous impact on Ethereum because it became so popular that there were so many transactions generated by players of this game that it literally bogged down the Ethereum network. So the Ethereum network could process nothing but CryptoKitties for a short time. Game isn't as popular anymore. It's kind of lost its early appeal, but it demonstrated one aspect of scalability issues that exist in any blockchain, which we'll talk about in a bit. All right, I think that covers all of Aki's questions, and it was a good introduction to the basics of Ethereum. So let's go check in the chat room and see what's going on. Christian has a follow-up question about proof of work in Ethereum. And Ethereum currently uses proof of work in a way that is very, very similar to Bitcoin's. It uses a different algorithm called ET hash or ETH hash. An ET hash is basically a variation of a proof of work similar to Bitcoin's SHA-256. But instead of using the SHA algorithm, it uses a combination of two algorithms called Dagger Hashimoto. And these two algorithms create a giant table in memory. And this table is a couple of gigabytes in size. And in order to produce proof of work, you need to hash together specific elements from within this table that you can't predict in advance. Those depend on the block. And the reason this was used as proof of work algorithm is because it requires significant memory, which makes it difficult or more difficult to implement on an ASIC that is pure computation, and is therefore intended to restrict temporarily Ethereum mining to GPUs instead of allowing the construction, the easy construction at least, of ASIC miners that would lead to industrial scale mining. So there are now some basic prototypes for ASIC miners in Ethereum. So once anything becomes profitable enough, then there's enough incentive to build an ASIC, but it certainly delayed that for a while. That's the proof of work algorithm. Within the proof of work algorithm, a lot of the same mechanics operate, meaning that you have to find solutions to proof of work algorithm that work kind of like the nonce in Bitcoin, and it also has a difficulty rating, and the difficulty rating dynamically adjusts in order to control how many miners participate and how profitable it is. So it gets easier if there are fewer miners, it gets harder if there are more miners, very similar to the difficulty retargeting algorithm in Bitcoin. All of these things happen on a different timescale in Ethereum, with blocks being issued in a matter of seconds instead of minutes, but the basic idea is the same. Now, the reward function works the same, meaning that each block has an Ethereum reward. However, there is a slight difference in how that reward is allocated to miners, because the Bitcoin proof of work algorithm is a winner takes all, whereas in Ethereum, there are winning blocks that found proof of work around the same time can also get a small share of the reward. So yes, all of that basically is very similar at the moment to Bitcoin. However, the proof of work algorithm in Ethereum has one interesting little twist, and that is called the difficulty bomb. And the difficulty bomb is basically that the difficulty on its own, if there is no change to the number of miners, keeps getting harder and harder and harder until it becomes impossible to solve blocks. And this was designed as an incentive mechanism to make sure that gradually mining was obsoleted, and instead Ethereum switched to proof of stake. That incentive mechanism hasn't worked very well because, unfortunately, due to the delay of proof of stake implementation known as Casper, the difficulty bomb has had to be defused on a number of occasions with hard forks in order to delay the onset of this exponential difficulty increase. Andrew asks, how serious is the issue of Ethereum blockchain bloat? From my understanding, fully validating nodes are almost impossible to sync up or operate without very serious equipment. What does fully validating even mean once sharding comes into play? All right, so Ethereum has a different level of scalability issues than Bitcoin, and these scalability issues have to do with the fact that in a smart contracts blockchain like Ethereum and all the other smart contracts blockchain, you're not just storing transactions, you're also storing contracts, and you're storing the data of each contract and all of the changes to that data. So when you're running a program inside a blockchain, you have to keep track of its memory effectively. You have to keep track of its state. So the actual state database of an EVM blockchain or a blockchain that runs smart contracts is an order of magnitude greater than the state database of Bitcoin. And we've already seen that, in terms of the growth of the Ethereum blockchain versus the growth of the Bitcoin blockchain over a few years. Ethereum started much later than Bitcoin, but then its blockchain data size actually became bigger than Bitcoin much faster. Now, as Andrew said, fully validating nodes are almost impossible to sync up or operate without very serious equipment. Well, there's two reasons for that. One reason has to do with the amount of data that you have to process in order to fully validate. The other reason has to do more with particular bugs that were found in 2015 that were miscalculations of the gas price, or vulnerabilities, if you like, in the gas price calculation. So some specific commands in the EVM were not priced correctly. And what does it mean to be priced correctly? Well, the purpose of gas is to limit and constrain computation so that you can't overwhelm the network with computation. So every operation should cost as much as it uses up in CPU and memory resources. And that's not an exact science, but there was an initial set of prices. And someone discovered that there were some commands that could be used to cause a much bigger use of resources without spending too much gas, which meant that an attacker could then create transactions that took a very, very long time to validate, and used an exorbitant amount of CPU compared to the amount of gas that was charged. And then the same thing also for data store, the ability to store a lot of data and not pay as much gas as expected. So some of these transactions were in fact created, and if you run a node with the software, the original software of Ethereum before this vulnerability was discovered, when it reaches these blocks, which are at about the 2 million height level, it starts taking 3 or 4 minutes to validate a block, instead of taking a tenth of a second or a third of a second to validate a block. Now, that's a very significant difference in performance. So if you try to sync a full node and you haven't set it up to ignore those vulnerable blocks, what will happen is it will sync up to block 2 million in about 30 minutes to an hour, depending on how fast your CPU and bandwidth are. And then it will get to about block 2.5 million, and then it will grind to a halt. And if you haven't done anything to that node, and if it doesn't have a lot of resources, that node could spend a month or 2 months just getting through the next 100,000 blocks. And so that's one of the problems. So the other problem is that in order to fully sync up and fully validate and keep a full copy of all of the state and all of the transactions in Ethereum, it requires downloading almost a terabyte of data onto disk. That's what a full archival Ethereum node is, one that doesn't discard old state. Keep in mind, when we're talking about computation within Ethereum, it's different from storing the state of transactions, meaning that once a contract has executed and its memory has changed, do you need to keep every copy of every memory state in the past? Not everyone needs to keep that. Only some nodes need to keep that. At least that's the logic within the Ethereum community. And as a result, most nodes, once they've validated past blocks, they discard all of the state of the contract that is no longer relevant, and they only keep the final state, which allows them to continue validating. And that's the difference between a full archival node versus a full validating but non-archival node. So when we say full node in Ethereum, that can mean two different things. One is, does it validate everything fully? And there are full validation nodes and also light validation nodes that simply look at checkpoints and go directly to the latest block. Or does it validate everything but not store everything? And then full archival nodes are ones that validate everything and store everything. And the difference can be quite significant. A light validation node can sync very fast, probably within a couple of hours on lightweight hardware, and can reach the current block, storing only 60 to 80 gigs of data on disk. A full validation node that doesn't skip over everything and jump to a recent block will take about 200 to 250 gigs on disk. And these numbers keep changing, of course, but that's just an estimate for now. And will take 2 or 3 days to fully sync. And an archival node that keeps all of the states and fully validates everything will take potentially a week or more to sync if you can keep it from crashing in that time and you have enough disk space, and it will consume more than a terabyte of disk to store a full copy of everything. One of the problems is that you need to be able to contact other full archival nodes so you can get all of the full information on every block, not just the headers, not just the summaries, but everything from the Genesis block. So that's why it's difficult to validate and fully sync an archival node. Let me check in the chat and see how things are going. We spent a lot of time on the first 3 questions, but this is the nature of discussing Ethereum. Is everybody still there? Did you fall asleep? So one of the concerns about scalability is what's known as the trilemma. A trilemma is a difficult choice between 3 characteristics where only 2 are possible at the same time. So compared to, for example, a dilemma, which we're all familiar with as a word. A trilemma, which exists in all blockchains, is the balance between decentralization, security, and scalability. So decentralization, security, scalability, pick any 2. You can have decentralized and scalable, but it won't be secure. Decentralized and secure, but it won't be scalable. Secure and scalable, but it won't be decentralized. And that's a classic trilemma. Now, doesn't mean it's impossible to achieve all 3. It just means that you have to compromise somewhat on some of them, and it's very difficult to achieve. It's easy to achieve 2. It gets very difficult to achieve even a portion of the 3rd characteristic. And it requires a lot more complexity to do that. So these trilemmas exist in every blockchain. In fact, they exist in life in general. Yeah, I used to be a consultant, and I used to tell people you can have high quality, you can have speed, or you can have low cost. Pick 2. That's a classic trilemma. I can do it fast and cheap. It won't be good. I can do it good and fast. It won't be cheap. Etc. So the trilemmas that exist in blockchains require complex solutions. In some cases, these solutions involve engineering a second layer. And this is the case with both Lightning Network and Bitcoin, as well as Raiden and Plasma and other second layer payment channel or state channel technologies that exist in Ethereum as well. It's the same concept. Basically, you have some security provided by special contracts such as multisigs and time locks on the base blockchain, and then you do the majority of your transactions off-chain between peers in a way that they don't have to trust each other because they have the security of the main blockchain, and that takes a lot of the load off the main blockchain. Another approach to scaling, which has been introduced in Ethereum, or at least in theory and in research at the moment, is called sharding. Sharding is something that has existed, of course, before Ethereum, and the idea is that you don't need to store everything everywhere and validate everything everywhere. What if you only stored a portion of the data in each location, and you only validated the transactions that were relevant to that portion of the blockchain? So essentially, you take the blockchain, all of the data all of the state that's in Ethereum or any other blockchain, and you separate it into shards. And each of these shards has a small subset of the total picture. When you want to validate a transaction, then you figure out which shard that transaction belongs to or corresponds to, and you send it to the validators that are part of that shard to validate. And then you have kind of an overall picture emerge by the coordinated information between various shards. Now, this is an old concept that's existed both in centralized and decentralized systems. For example, if you have a search engine, you don't have one computer that does all of the searches. And how do you split up the searches? Well, one of the early ways of doing that was to break searches into shards. So if you search for anything between Apple and chocolate, you get the shard that manages all things that start between A and C. If you search for anything between danger and foxes, you get a different shard, which manages the letters D, E, and F. Now, that's a simplistic way of doing it. A more sophisticated way involves using trees, and these can be either binary trees or index trees. And an even more sophisticated way is, instead of doing it alphabetically, based on the string that you're looking for, you shard things based on their hash. That's called a distributed hash table, and it's how things like BitTorrent and Napster and Gnutella worked. So computers would store only some files in a distributed file storage network, and the way you would find where that file is stored is you would look at its hash, and then you would look at a hash table that broke down hashes in a tree, so you could find where that shard was. Now, a very similar plan is in place, and there's a lot of research going on, to combine sharding with proof-of-stake, Casper FFG as it's called, in the near future for Ethereum, so that both sharding and proof-of-stake are introduced at the same time, because they're very complementary. And the idea here is that you would have computers that would participate in the Ethereum network, but they would only manage one shard, and you would split the Ethereum data store or state into hundreds, thousands of shards. And let's say, for simplistic purposes, if your address starts with 00, then you're on shard 0. If your address starts with 01, then you're on shard 1, all the way through address FF, in terms of the first 2 hexadecimal digits. And then you're on shard FF. And just like that, you have 256 shards. Now, if you have a transaction from address 1 to address FF, both address 1, shard 1, and shard FF have to participate in that, right? And they would validate that by exchanging information across shards. So that's how sharding works, or how it's planned to work, because it hasn't been implemented other than in prototypes for the time being. Of course, the difficulty in sharding isn't the storage of the data. We've already done that. It's been done in distributed systems for decades. That's not the difficult part. The difficult part is, how do you apply consensus validation on a sharded data store, and how do you make sure that no one can attack the consensus mechanism by taking over a shard, which is a likely possibility. So that's the problem that needs to be solved in sharding on a blockchain. Francesco asks, and let me check in. Still here. Hello. Hey, hey, hey. Okay, great. Everybody's there. Fantastic. Francisco asks, is it possible to recharge Ethereum gas of a smart contract after it has not anymore to run? Or do you have to switch to another smart contract when you run out of gas? So this is an important question, but you have to understand some of the fundamentals of Ethereum in order to better understand how gas works. And it's a very complicated topic, and it's often the most confusing part of Ethereum. So the way Ethereum works today, contracts don't have gas. Contracts don't store gas. Contracts have Ether in them, but they don't pay for transactions, and they don't pay for the gas that they consume. Instead, when you construct a transaction that engages a contract, that is addressed to a contract, that transaction itself has to have a gas amount in it, which you pay in Ether from the originating account, meaning the account that creates the transaction, the from account in the transaction, has to have enough Ether to pay for whatever the maximum amount of gas times the gas price you're willing to pay in that transaction for all of the execution that it's going to cause. So you create a transaction, you say, I'm going to allow up to 100,000 gas in this transaction, and I'm willing to pay up to 2 gigaway per gas unit for my prioritization of my transaction. Great. So that means there's 200,000 gigaway worth of Ether has to be in the from account. Once that is validated, the EVM will deduct that. It will deduct 200,000 gigaway from your from account. It will start running the contract you wanted it to run. Maybe that contract calls another contract. It will keep counting how much gas you're spending. And then you call another contract, and then you pay to an address, et cetera, et cetera, et cetera. All of this gas is deducted from the 200,000 gigawatt. Of course, if you run out, the EVM will spit back the transaction to you with insufficient gas. Now, if you don't run out, if you consume 180,000 gigawatt worth of gas, or in this case, 90,000 gas units, then the EVM will refund back to your from address the remaining 20,000 gigawatt that you didn't spend for your transaction. So contracts don't contain gas. The gas has to be supplied by the transaction that called them. Now, this is something that may change in the future. In fact, there are proposals to allow a contract to pay for the gas that it consumes. And this is because it will simplify certain types of operations. Imagine, for example, that you just bought a wonderful token from an exchange, and you now own this token, and you have a wallet that's holding this token. And you don't know this token is an Ethereum token. You bought it thinking it was something else. You are involved in the CryptoKitties game, or you want a Gnosis token, or whatever. And you received it from the exchange, fine. And then you try to spend it, or transfer it, or do something with that token. And suddenly your wallet says, not enough Ether to pay gas. And you're like, what's Ether? What's gas? I didn't know I was involved in Ether. I just had a CryptoKitty. What's this Ether thing? And what's this gas that's needed? So even though you're operating on a token that's running on top of Ethereum, you may not know that it's running on top of Ethereum. You may not care. And so if anytime you own a token or some other asset or system that's related to Ethereum, or running an application that's running on Ethereum, you have to have Ether in order to pay for any transactions you create. Basically, any application you run on Ethereum, you have to have Ether in your wallet to pay for the gas. Well, this causes a lot of confusion to new users. This also makes it very difficult for application programmers to correctly balance the usability of the system. So wouldn't it be great if the CryptoKitties contract could charge you in a different token, or if you were transacting the Gnosis token, you could pay the fees in Gnosis instead of Ether. Or if you were transacting in whatever other token, you could pay the fees in that token, or the contract could pay for you, and that's included in the cost of buying the token first. So that may change. In the future, we may see contracts be able to pay for gas. But right now, the gas has to be paid by the transaction that originates any execution. Richard asks, how do I find the genesis block of any specific ERC token? And how do I find the specific metadata showing its name, creation date, etc.? Richard, ERC tokens don't have a genesis block because they don't have a blockchain. Instead, an ERC token is instantiated as a contract. So an ERC token is a contract. Everybody's ownership of a specific ERC token is recorded in this contract. So for example, let's say I create Andreas token, and that Andreas token is going to be a contract that implements the ERC20 standard interface, which means it has some functions for transferring tokens and for recording who owns how many tokens, how many Andreas tokens. So there is a contract that corresponds to Andreas token. In order to create that token, I have to create that contract. So I'm going to take an ERC20 contract, compliant contract. I'm going to put in the name of my token and how many units it's going to have and how divisible they are and what the symbol is. And then I'm going to compile that contract, and I'm going to create a transaction that records it on the blockchain. And from that point on, if anybody wants to own Andreas token or transfer Andreas token, they have to do a transaction with that contract. All of the tokens live in that one contract. So any transactions to do anything related to that token will have as their to address the contract that created it. And that contract contains within it the information about what the token's called, how many units it has, whether it's divisible, and what the symbol is. Those are the standard interface components of an ERC20 implementation. Now, there are some proposals as well as some implementations for what are called token registries, which are contracts that keep track of what tokens exist and what their contracts are. So you could have a centralized contract, which is basically a name service or registry, where you can register your token after you've created it. And now that registry knows that Andreas' token is at address 0x blah, blah, blah. And that means that if you want to find out more about Andreas' token, that's the address you talk to. Another way to think about this is, of course, if you have a name related to it, which you could do through the Ethereum name service, you could find all of these details about a token. Arnd asks, how can Ethereum become a platform for worldwide computing of smart contracts if the simple application of CryptoKitty can already bring it to its knees? Great question, Arnd. And of course, that's a question that a lot of people have asked, and it's the same fundamental question that people ask about other blockchains, which is how can this ever become successful if application X brings it to its knees, or if adoption or exuberance around its price brings it to its knees or drives the fees up? Let me rephrase your question and hopefully answer it that way. How can the internet become a platform for worldwide video distribution when sending a single JPEG shuts down the entire network of my university, said Andreas in 1991? Well, that would have been the case at the time. If I tried to transmit a video across my university network LAN, which at the time was 1 megabit per second Ethernet, across the campus, and that was considered super fast for those days. Now, that would melt down my university network, and it certainly would overwhelm the transatlantic connection that was connecting my university in England to other universities in the US. So the reality is that when you create a new technology platform, when any new technology platform arises or is invented, it can do certain things. And when people try to push the platform to do more things, it causes a scalability challenge. Basically, it fills up. And when it fills up, things stop working as they should. And that causes people to invest in infrastructure. So they start building better infrastructure to increase the scalability, but also the usability and ease of use of that platform. And once that frontier is moved, new applications become possible. And of course, if you're an engineer, as soon as new applications become possible, you write a of the system demonstrate these new applications, and you run out of capacity again. So that causes more investments in infrastructure, more implementation changes, more optimizations in the protocols, et cetera, et cetera, et cetera. And that never ends. It never ends because the more you can do, the more people will do with the infrastructure and will push it. So can Ethereum become a platform for worldwide computing of smart contracts if the simple application of CryptoKitties can already bring it to its knees? I think the answer is yes, simply because it's important in engineering to never say never, to never say that something is impossible just because it can't be done today or because we don't know a way to do it today. That doesn't mean it's impossible. It just means it's not currently possible. So today it can't be a worldwide smart contracts computing platform, but that doesn't mean it can never be that, or it doesn't grow to be that. It simply means that today it can only do certain things, and those include running CryptoKitties at scale, but nothing else at the same time. Mirza asks, considering the current version of Casper v2 requires a minimum of 32 ETH deposit to be validators, how is this affordable for the average person compared to proof of work? Mirza, it's more affordable than proof of work in some ways because the investments you need to make in proof of work requires capital investment. You have to buy a whole bunch of GPUs or ASICs or whatever else. It requires installing that equipment in a fixed geographic location and consuming power from the utility network. All of that involves significant risk. The GPUs break down, they overheat, you run out of space, you run out of power, you have to keep maintaining them, there's network failures and disconnections. All of these risks increase your costs of running proof of work. In some ways, proof of stake is more simple in that the cost and risk is limited to the specific stake that you've put down, and you have to deal with fewer moving variables. But yes, a minimum deposit of 32 Ethereum, 32 Ether is quite a significant investment. But you don't have to do it alone. And that's the other important thing to consider. Whether in proof of work or proof of stake, the reason proof of work can continue to work even for small miners is a thing called pooled mining, where people join forces together and that way they have a better chance of succeeding. Well, you could also do that by pooling stakes with other people. And so one of the expectations is that Casper, or whatever it's going to end up being called, proof of stake mechanism on Ethereum, will allow people to pool their resources together in order to participate in proof of stake mining. Oh, okay, I see we had some problem with the video and audio. Are we back? Let me know in the chat if we're good now. There's a slight delay, about 30 seconds between me asking you to tell me if it's okay. Ah, there we go. And there it is. All right, let's move on. Mario asks, Ethereum's platform appears to offer an innovative platform for token and ICO applications on top of its decentralized blockchain. Does it lose its focus by attempting to host any general smart contract application? For example, business rules, middleware. Mario, I would hope that Ethereum isn't just for ICOs and token applications. I think that's a very obvious and interesting application, but it's not the most interesting application. In my opinion, the governance application, which is using smart contracts to govern organizations, either human organizations, machine organizations, or human-machine hybrid organizations that reinvent the modern corporation, that give you business rules that are transparent and auditable and open, decentralized, global, neutral, censorship-resistant. I think that's a very, very powerful application. I think it's the most powerful application. Tokens and ICOs are a subset of that, and they're appealing because of all of those properties. But I don't think that is the focus. I don't think most of the people who are involved in developing for Ethereum think that that should be the only focus of Ethereum. So I don't think Ethereum loses its focus. Its focus has always been to be a platform for computing, general purpose blockchain, programmable blockchain for computing smart contracts. And I think it should be doing more than just tokens and ICOs. Let's switch tracks now and talk a bit about some other chains. And I'm going to answer a few quick questions here. David asks, did Bitcoin Cash live up to its purpose? It's difficult to say because purpose is something that implies that there is a single, easily defined purpose that one person decides or one organization decides, and that doesn't really work that way with blockchains. No matter what some people might say their reason for building something was, that doesn't mean that's what the market does or that other people weren't involved for different reasons. So it's very difficult to say what the purpose of a system like this is, but we can say, compare it to what the expectations of people were. I think Bitcoin Cash succeeded in presenting an alternative path for development of scalability solutions within the Bitcoin space. So now we had two very different approaches to scaling Bitcoin. One was the off-chain now, on-chain later, and the other one was on-chain now, off-chain later. And really, those two sides were never able to agree and come to a single path for scalability. So now we have two chains that explore both of those paths independently with independent development teams and independent currency units. And that means that people who are interested in exploring a different path are able to do so. And the market is able to choose between them and evaluate each's success. I think it's premature to say if anything has achieved its purpose, not just Bitcoin Cash. I think it's premature to say if Bitcoin has achieved its purpose. And that's been running for 10 years because these systems are constantly evolving. And the market around them is evolving. And the environment and users are evolving. And the expectations and applications are evolving. And during all of this evolution, there is no fixed point at which you can put a stake in the ground and say, okay, now let's see, has it succeeded or not? There's no deadline. There's no date by which success must be achieved or otherwise it's a failure. There's no metric by which success must be achieved. You define success, and the metrics of success vary, and they vary over time as well. We might find that it turns out that people wanted to use these platforms for different reasons than we thought a few years ago. And that's okay. That's the market responding to innovation. So really, whether Bitcoin Cash lived up to its purpose is a subjective question that is answered by each individual. So I'll throw the question back at you. David, has Bitcoin Cash achieved its purpose for you? Are you using it for the purpose that you want to use it? And does it work for that purpose for you? And every person answers that question about every blockchain independently. And that's what the marketplace is. David also asks, given that stablecoins are not regulated, why should anyone trust a coin that claims to be asset-backed? David, that's a really good question, and it is very difficult to answer. I would take it one step further. Even if stablecoins are regulated, can you trust something that claims it's asset-backed? There are lots of regulated things that claim to be asset-backed, where we have had scandal after scandal after scandal, where upon audit of the location where the assets are supposed to be, there are no assets, or there's been a fractional ownership situation whereby there are 10 assets, but there are 20 people holding certificates claiming to own one asset. So essentially, the asset has been oversold or hypothecated. So regulation doesn't ensure trust. Although regulation can provide the rules by which you can build trust, it's other mechanisms that are used. Asset-backed stablecoins have a fundamental problem of centralization, meaning that you have to trust someone. In a virtual asset like Bitcoin or Ether or other assets like that, you trust the network rules, you trust the consensus, you trust that the system is operating as it should. You don't trust any particular person or organization. In a stablecoin situation where you have some kind of asset, and that asset is held by a custodian, that is not a trustless system. That is a system where you have to trust the custodian. So how does the custodian earn your trust? Well, they can refer to regulations that show the regulations themselves don't create trust, but they can provide mechanisms for trust. For example, repeated audits by independent third parties verifying, one, that the assets are there, and two, that the assets versus liability balance sheet of that organization adds up. Because it's not enough to simply say, do you have $100,000 in the bank account versus the 100,000 stable dollars that you've issued? Because you could have $100,000 in your bank account, and then you could have two $50,000 loans that you've taken out against those, which means that you actually own nothing. you have liabilities that match those assets, and so your net assets are 0. So in order to validate, you have to also count the liabilities that you have, and that's not always easy. There are now some stablecoins that are in regulated markets. Your next question addresses that. David asks, is there a case for a stablecoin to be issued from a jurisdiction that regulates blockchains, for example, Gibraltar or Malta, to give users the assurance that they may require? It's not enough to regulate the blockchains. You need to regulate the actual custodian in a way that ensures that they have some mechanisms for trust. And even then, there's an element of risk, and that's called third-party or counterparty risk, that the custodian doesn't have these assets or has extended liabilities that are unknown to you, that they've used the assets to back these liabilities. So there are a couple of jurisdictions now, for example, New York, under the Department of Financial Services, which regulates certain companies that operate in New York. One of those companies, Gemini, has issued Gemini dollar, which is supposedly a stable coin that is in a regulated environment and backed by some process that you can trust that it's full reserve with without assets exceeding liabilities exceeding assets. There are others, and just in the last month, 2 or 3 stablecoins have launched, and I believe that they are in regulated environments. Again, don't assume that regulation equals trust. Regulation is a means towards building trust and a set of standards for building trust, but it's not foolproof. Bernie Madoff was very regulated. Exxon is regulated. Enron was regulated. Every Ponzi scheme that's happened in the last 100 years was in regulated markets, and yet they happened anyway. Eric asks, what are the unique features and trade-offs of DAGs, directed acyclic graphs, compared with Bitcoin, Ethereum, and Monero? And follow-up question from Marcel, is IOTA's Tangle an alternative to proof of work or proof of stake? So I've learned a bit more about these blockchain alternatives. And I think one of the confusions that I had in the past, and that others have helped by pointing it out, sometimes gleefully while laughing at me, is that DAGs themselves are not a consensus mechanism. DAGs are the data structure for underlying a consensus mechanism. Just like blockchain isn't a consensus mechanism. You can have blockchain with proof of work. You can have blockchain with proof of stake. A blockchain is just a chain of blocks. A DAG is basically a directed acyclic graph of blocks, meaning that it's, or transactions directly. It's not a chain of blocks, and it has some different characteristics. Probably the best example or most well-known example is IOTA's Tangle, and what you have there is transactions related to each other in kind of parallel chains that get merged together by a consensus algorithm. Now, tangles can work with proof of work. They can also work with proof of stake. Theoretically, at least, there's no reason why you can't apply different consensus algorithms to tangles. What these do are they implement scalability improvements. There are some subtle relationships between the use of DAGs and, for example, the sharding proposals that are being suggested in Ethereum. Again, these are scaling solutions of the underlying data structure. The claim here is that using a DAG or Tangle specifically gives you a greater transaction per second processing ability and lower confirmation times because you can actually push more capacity through that data structure. And again, it's not related to, you could do that with different consensus algorithms. So that's about all of the knowledge and opinion I have on DAGs. It's a topic that I haven't researched in great detail, and so I probably got some of the details wrong. I apologize. This is a very big space, and it's not often easy to have good information on everything. It's impossible, in fact. All right. I think that completes everything. We had a few questions we didn't get to, but we can either complete those offline or respond to those in our next session. And thank you so much for all of the great questions you provided today. This has been session 7 of the 10th iteration of the Massive Open Online Course, or MOOC, for the University of Nicosia's master's degree in digital currencies. I'm Andreas Antonopoulos, and I've been answering your questions from the last week. Please ask more questions. Ask them in the forums. Talk amongst yourselves. Comment throughout the week. And I'll see you for the next session, session 8. Thank you.